Hello, this is Lab 1 on constant velocity. Constant velocity is a linear line on position versus time graph and a straight line on the velocity versus time graph. For constant velocity to exist, there must be an F net equal to 0. Constant velocity leads us to the momentum principle. The momentum principle is delta P equals F net delta T. It allows us to derive and use very many useful equations. Let's derive an equation for velocity. Delta P can be rewritten as P final minus P initial. The P's can also be rewritten because P equals mv from Newton's second law. Therefore, the P's become mv final minus mv initial, respectively. Now divide by mass in order to isolate velocity. We can do this because we assume the mass is constant. This then gives us velocity final minus velocity initial equal F net delta T over m. Finally, add the initial velocity. This gives us an equation for velocity. This is important because when F net equals 0, V final equals Vi, proven constant velocity. Now let's try this idea out in the real world with my robot. This is my robot. It weighs 0.493 kilograms. Just to give you guys some perspective, here's the actual robot. I used Tracker to track my object across the screen. The first thing I did was I set a coordinate axis right here, and I set the origin right at my starting line. That way I could get a fresh as far as it goes in one direction. And my axes are oriented. This is the plus X following my mouse going to the left. The minus X is going to the right following my mouse. Plus Y is going up. Minus Y is going down. The plus Z is coming out of the screen towards us. And the minus Z is going into the screen. I use the reference line of a ruler, and it's 12 inches. That equivalates to 0.3048 meters. And let's just watch it go across the screen real quick. It goes for 3.623 seconds, and it travels approximately 0.844 meters in the plus X direction. It also says that it travels in the minus Y, but I think that's actually due to error of my center of mass not clicking the same exact spot on the Y every time. Let's make a free body diagram. The robot has an initial velocity going to the left, but we can't forget about friction, which is opposing it going to the right. There is also gravity, which is pulling the robot down into the table. The final force is the table pushing up on the robot, which counteracts gravity. The robot is simply relying on the initial velocity that it had in order to go forward to the left, because the net force equals 0. The free body diagram illustrates the point that the net force equals 0 because all the arrows cancel out each other. Let's now look at my Python code for the computer module. My initial conditions for this was for the ball was 0.4938 kilograms, the ball's position because it's only moving in x was 0.001, and the velocity was 0.232687. Here is the velocity equation that we derived earlier in my code. Again, here we see F net equals 0. Therefore, the final velocity equals the initial velocity, meaning constant velocity is in effect. Let's run the code. By these two figures, you can see that the position is always increasing. This is verified by the displacement. The velocity is also seen constant by the position versus time graph having a linear line. Module of my robot's position versus time. The blue is my tracker position, and the model is the red line. As you can see, the red line is a lot straighter than the tracker. I believe this is due to errors in clicking on the Y once again and the X not being in the exact same center every single time. If I were to flip my X-axis, then my plus X would be going to the right and my minus X would be going to the left. This would give me an opposite position of my graph, so my time would be above the position and the lines would be flipped over the X-axis, so going down and not up how they are. At first, tracker starts ahead by 0.004 at 0 seconds. The graphs end with Python ahead 0.0017 meters difference in the end at the very end of the graphs. The major difference between the two graphs is that the Python is straight and linear the whole way while the tracker goes down and then back up. The discrepancy between the two causes a small source of error because I wasn't clicking in the right spot every time during the tracking. In conclusion, my robot underwent constant velocity. The Python model appears to be a more accurate representation of the data, although not by much, as there was only a small discrepancy. Even though the discrepancy occurred, the Python tracker only ended 0.0017 meters away from each other at the very end. Both of these methods, tracker and Python, are useful tools in physics. Thank you for your time and thank you for watching.